Hello, my name is Matthew Tannehill, and this is my presentation on Ada 2005. Ada 2005 is a modern structured, imperative programming language that a programmer chooses when faced with a mission-critical system that must work all of the time. It has all of the features you would expect to find in a modern programming language, like an object-oriented design, a generic container library to draw from, a high level of abstraction, and concurrency, just to name a few. But the area in which Ada 2005 is said to excel is where safety and reliability are primary concerns. It is a very robust language, and therefore this ensures its stability. Ada was named in honor of Augusta Ada Lovelace, the daughter of English poet Lord Byron. Ada Lovelace is considered by many to be the world's first programmer for her work with Charles Babbage on his analytical engine. I found it refreshing to see the name of a language give respect to its field, unlike other languages named with no imagination, like, well, the last one was called B, so let's call this one C. Or, I think I will name this language Oak, because that is the kind of tree outside my office window. In order to understand Ada 2005, you have to understand the origins of where it came from. In the late 1970s, there was a need by the Department of Defense, the DoD, for a single programming language that could meet all of the requirements for programming the various projects the DoD was involved in. The DoD concluded that if there was a single standard language for future projects, this would save them a great deal of money. After researching the languages that were available at the time, it was decided that no programming language could adequately meet the language requirements the DoD wanted. A competition was held to see who could develop a language that could meet these requirements that were defined as the Steelman language requirements. The winners went on to develop the Ada language with the support of the DoD. Ada was developed by an international design team from C11 Honeywell Bull and led by the developer Jean Ichibiach, a Frenchman. To realize how important it was to include international involvement in the design of Ada, you could say the French designed the programming language we would use to write the software for American defense. Ada was originally based on the Pascal language and designed to be a common high-order language that solved many of the weaknesses of the Pascal language. Some of the main design goals were to be defined through reliability, contain code that was easy to write and maintain, include extensive error checking at compile time and runtime, and to work well in embedded and real-time systems. With the backing of the DoD, Ada was very successful and was standardized in 1983 by the American National Standards Institute, the ANSI, and then later internationally by the International Organization for Standardization, the ISO, in 1987. In 1988, it was decided that Ada needed to be revised to include modern programming technologies. A software designer named S. Tucker Taft of Intermetrics led the redesign of Ada, backed with the support of the DoD once again. Again, the international community was consulted to see what was needed for the modern version of Ada, so that not just the defense community's needs were considered. After some time, the requirements for the revision were established by the Ada Joint Program Office, the AJOP. This effort would be completed in 1995 and become known as Ada 95. Ada 95 was designed to ensure backward compatibility with Ada and inherit all of the features that were designed into Ada with the addition of several new ones. There were three major features that were included in Ada 95. The first, object-oriented programming, which was not fully implemented in the original Ada because at the time the designers did not foresee the popularity of this program methodology. The second was hierarchical libraries. This was a need to update the flat nature of the library system to allow for more visible control between libraries and reduce compile times. The third was protected types. This was essentially used to complement the current rendezvous system of synchronous message-oriented mechanism with an asynchronous data-oriented mechanism. With the completion of the revision of ADA, now ADA 95 was accepted by the ANSI and the ISO, and has the honor of being the first internationally standardized object-oriented programming language. A few years later, the DoD had stopped funding ADA 95 to pursue other programming options like off-the-shelf components, and in 2001, the ISO called for a revision of ADA 95. ADA 95 was revised into ADA 2005, and most of the support came from volunteers, with S. Tucker Taft still providing a lead design role. ADA 2005 is a minor revision of ADA 95, which just further extends many of the features added originally in ADA 95. ADA 2005 remains backwards compatible with both ADA and ADA 95, so that it may enjoy the features that made its predecessors a strong programming language, while extending the functionality of these features with modern technologies. In 2007, ADA 2005 was officially accepted by the ISO. ADA 2005 can best be described as ADA 95 that has been tempered with time and polished with experience. ADA is a strongly typed language model. This gives it the ability to detect most errors statically at compile time, and then many of the remaining errors dynamically at runtime. With such a high detection rate of errors, this helps save a lot of time debugging. The syntactic design of the language, which was borrowed mainly from Pascal by the original ADA, makes for a model of coding that utilizes a write one time and read many times. This is designed to ease future maintenance, and less time is spent on maintenance is a cost savings in the long term. ADA has excellent runtime checking and exception handling. ADA 2005 performs extensive checking at compile time and also at runtime to ensure the highest number of errors can be detected. If an error does occur, the built-in exception handler can take over execution of the program and deal with the error. This reduces the probability that a program will crash from an unexpected input or error in the code. ADA 2005 supports object-oriented programming. This provides encapsulation through use of packages, inheritance through use of derived types, and polymorphism through class-wide types, and type extension through record extensions. Since the object-oriented programming features were built by extending existing parts of the language, the programmer has the option not to use the object-oriented programming methodology at all in development. This allows for multi-paradigm designs and concurrency and parallel processing. This style of programming is more error-prone than the sequential programming, but ADA 2005 does it well by using protected objects to help share data and tasks. To manage concurrent activities, it implements a rendezvous feature to manage task synchronization. This also allows the use of more than one CPU core simultaneously, while processing instructions and data to increase efficiency of the program execution. For ADA 2005 to handle modular programming, it features packages, which allow functions to be independent and interchangeable. By being able to compile packages separately and without implementation, it's easier to debug specific parts of an application. This piece-by-piece construction allows for easy development of a large system. ADA 2005 can easily interface with other languages because this was a design goal of the original ADA language and built into it. ADA 2005 then inherited this mature feature from its predecessor, allowing for no middleware needed to accomplish this. ADA can send and receive data directly from other languages nested in ADA 2005 code. This simplifies the act of writing a program because the code does not need to be exclusively in ADA 2005 and therefore does not sacrifice efficiency where another language might be more appropriate for the functionality. ADA 2005 features generics. Generics are a standard library of packages that provide many common services needed to program. ADA 2005 extends this library by adding generic containers in addition to the standard library. ADA 2005 does not allow for special cases of its library and uses a strictly controlled syntax and formal parameters in the syntax in its library to maintain its advantage of predictable and safe software. ADA 2005 was designed to be portable. It is a very mature language that has been greatly standardized since its original version. It has been designed with platform independence as a goal. These qualities allow it to be easily adapted to new systems and new platforms with little modification of the code. ADA 2005 specializes in safety critical support. It achieves this by allowing the programmer to look at features given and define restrictions to those features. This allows the programmer to exclude any part of the language that may be possible hazards to the area of safety in a program. A good example that was designed with ADA 2005 is the Raven Scar Profile, a collection of restrictions of ADA 2005 features which allows for simple certification of high integrity systems. One of the most difficult parts of the ADA language was to have the compiler validated. The original designers of ADA required it to be able to be used to design large systems that were reliable. This meant in order to have many different programmers working on the same project and each of their work products to be easily integrated together, there needed to be a high level of standardization. By requiring an ADA 2005 compiler to have to pass a validation test, it can be ensured that safety critical software can be easily validated with predictable code caused by a high level structured language and standardization. With ADA 2005, the ADA core was developed to encompass all of the main features required by the programming language, yet still keep its integrity. The core can then be extended with annexes. An annex can be developed with specialized needs in mind, so ADA 2005 can be adapted to the requirements of the system. This method allows the ADA core to be as robust as possible and still allow flexibility in the application of the language. This method also makes compiled code more efficient because you only pay for what you use. ADA 2005 has found a niche in today's market. Given that it excels in safety-critical application domains, other government and private agencies have started using it. For example, NASA satellites and other outer space equipment are all programmed using ADA. Air traffic control systems, high-speed rail systems, avionics software aboard aircraft, and financial software are all programmed using ADA. ADA 2005 is a good choice where software failure would be devastating. All of the features that ADA 2005 provides, like strong typing, a highly structured language syntax, extensive runtime checking, and built-in exception handling, are the primary reasons that make it so reliable. There is very little room left for an error to actually crash the system unexpectedly. Also, with each of these features being designed for a high level of standardization, they are extremely predictable in their behavior. This predictability gives it the ability to have a safety-oriented goals met by design. These designs are shown as the basic building blocks when you look at how packages, protected objects, generics, and visibility of data all interact, and other features like object-oriented programming, concurrency, parallel processing, and portability.